Okay, now let's go for sometimes people also, as we said, post tensioning, people also do external post tensioning, right? I said external post tensioning means the pre-stressing steel will be, it can be within the cross section like this also, right? But sorry, this is CGS, right? Here you see this is internal pre-stressing, these are the strand which is within the concrete. Now, in external pre-stressing steel is outside the cross section, in the sense which is not within the concrete, it is outside the concrete, right. So, what are the things? So, if you see here, the amount of pre-stressing moment that I generate is nothing but the distance, the force multiplied by eccentricity of the cable. This is your pre-stressing moment. Now, in this case, if you see, the eccentricity is measured always from CG of the cross section to the strand. I should say CG of the concrete, okay, CGC, right. Now, if you see, in this case, this is the force that I put, F into E1 equal to MP. In this case, if you see, if in the case of an external pre-stressing, my cables are inside. Now, this E2 is less than E1 because I am keeping it outside, right, the cross section. So, what would be the force moment that I am generating? F into E2, which is going to be MP. Now, this MP2 is going to be less than MP1, which is this. So, I am not getting more, even though I am putting same amount of pre-stressing steel. If I am keeping this within the cross section, but outside concrete, then the moment that I am getting from pre-stressing will be lesser if I am putting steel within the cross section. So, which is not efficient. So, that is the reason people innovated and they say that, okay, somehow I create high eccentricity if I am able to push this cable outside by creating eccentricity E3, which is higher than E1 and E2, then I generate more pre-stressing moment, which will help me to reduce the amount of pre-stressing steel that is required. So, that is why external pre-stress concrete bridges have lower flexural strength. Okay, that is what this is. This is the one, right. So, this is a conventional external pre-stress. That is the reason we go for highly eccentric external pre-stressing. So, somehow the whole idea is I want to have more eccentricity of pre-stressing cable with respect to CG of the cross section. Now, how do we do that? So, if I do that, I put more pre-stressing moment that is going to offset the moment that is coming from external loads. That is the idea, right. So, this is the way that engineers they do, right. This is the original external tendon, always it is within the cross section only, but outside concrete, right. It is within the cross section, but outside concrete. So, you have to be careful, okay. So, if it is an internal PT, cable will be within concrete, but here within cross section, but outside, right, like this in the figure that it is shown. So, this is the way they create a deviator block and then they run the cable profile. But the disadvantage with this system is the eccentricity what I generate is going to be less. Now, if somehow I can create this kind of a deviator block somehow only at specific locations, then I can run the cable even outside the cross section like this, and then that will help me in more eccentricity than that is possible for a conventional external system. So, this is called high eccentric external tendon, which can help you in optimizing the design quite well. So, for example, this is a continuous system that you see here, and this is the typical bending moment diagram that you will get, negative moment at support, positive moment at midspan and so on, right. So, my external tendon layout also should follow that, right. If somehow I am able to generate more eccentricity, then I can design very lightweight structure due to reduction of the girder height, because now I can keep small height and I can run the cable outside at a high eccentricity somehow by creating this kind of a deviator blocks, right. So, then you effectively use materials and there is a flexibility in design to suit various site conditions. So, for example, this is one nice pedestrian bridge they have done over Shimazaki river in Japan, and you can see very elegant design. It is a 2-span continuous system, and you see the cable profile is outside the section and it also goes like this, and then what they have done, they have created a nice fin like to make it aesthetically splicing. So, with this kind of a design, they were able to reduce the weight of the superstructure by going for high eccentric tendons, and it has a fin back that is basically covering the eccentricity portion with intermediate fulcrum to create more aesthetic appealing pedestrian bridge like what you see here, right. And this is again a very interesting structure from India. This is a Nagpur flyover, double decker flyover. You see here there is a metro train that is running at the top, and then there is a road bridge that is at the bottom. And this is a spine and wing construction, okay. This is spine and wing construction. Again, they are all PT. Their segments are cast, and then they are run PT cable from one end to another end. They are prestressed together to form this, and then these elements are cast separately, and then they are attached again separately. And this is a typical box girder segmental construction. Box girder segmental construction. So, again, so this kind of innovative things can be done using prestressing. And the splicing that we already talked about, I can create a pre-tension beam in factory. This is also pre-tension beam. Now, I can connect these two pre-tension beams by running a cable through them, right, and then do the post-tensioning. So, I can create a spliced large length girders by using pre-tensioning and post-tensioning. Now, this is one thing that again we have to keep in mind. When you go for post-tensioning system, cable run from one end to another end, and if there is a change in the cable profile, typically if you take the cross section, let us say at this location, if you take at this location and you look at this cable, and you see here that the strands within the duct tries to move up, okay. So, actual eccentricity, we want the center of all the cables to be within the center of the duct, but the tendency will be exactly opposite. At the bottommost location, at the sagging point, I want these cables to be as below as possible, then only I get more eccentricity. But because of the virtue of the profile, when you do the tensioning, these strands will try to move up. So, that will reduce the eccentricity that is available for me. Similarly, at the support location, what will happen is this cables, strands will try to move inside the duct, okay, and in this process again the eccentricity will come down, okay. So, for depending upon what kind of system that you have, usually the manufacturer and vendor will give you what should be the correction that you need to do for that. For example, these are the different tendon sizes. This is a number 13 mm strand, which is typically a half-inch strand, and this is a 15 mm strand. It is taken as 0.6 inch strand, and you have these kind of varieties are there: 3 strand cable, 4 strand cable, 7 strand cable, 12 strand cable, 19. This 19, 22, 31 are very commonly used, okay. And when you go for 0.6 inch strand, you have again 3 strand cable, 4 strand cable, 7 strand cable, 12 strand cable, 19, 31, 55. And accordingly, you know, larger the number of strands, larger will be the sheath diameter, the duct diameter. Sheath is nothing but the duct, right. And similarly, what should be the eccentricity that I need to correct, and this eccentricity is the correction. I think the correction we need to do, okay, from the actual CGS, okay. So, how much we need to correct is again given by this reference, okay. You can use this reference and then accordingly you can correct, because again when you have huge force, even a small reduction in eccentricity will reduce the prestressing moment that you are applying on the system, that we need to be careful, right. So, anyway, in unbonded post-tension system, they differ from bonded post-tensioning system by providing each individual cable permanent freedom of movement relative to the concrete. One big advantage in unbonded system is I can take the cable out and put another cable after some point of time, or maybe go for a larger diameter also. Again, each individual tendon is coated with a grease, generally lithium based, and they are covered by a plastic sheathing as we have seen in the previous slide. And the transfer of tension to concrete is achieved by steel cable acting against steel anchors in the perimeter of the slab or on the beam, right. The main disadvantage over bonded post tensioning, that is, cable can de-stress itself and burst out of the slab if damaged. And typically these are done in flat slabs. Post tension slab systems are quite common. Unbonded systems are quite common. And if you are not careful, it can de-stress and then it can burst out of the slab if the slab is damaged. Okay, such as repair. While you repair some slab or if you create some opening, if you are not careful, you may damage the cable and then it can burst out. Okay, this is the problem in an unbonded system. Again, external post tensioning is again commonly used for structural strengthening as well. As we have seen, when we say external PT, the PT cable has to be outside the concrete, right? And advantage with this is we can possibly monitor and replace the tendons, and it also help in better concreting, and that will ensure better concrete quality, and we can also use narrower webs. It can help in optimizing the design. Nowadays, they are increasingly used in construction of new bridges, and it is also primary method for strengthening and rehabilitating existing structure. This is very, very important. If your structure has deflected, the only way we can address the deflection is by external PT. No other method can actually help you in recovering the deflection. Okay. So, whenever you have a structure with deflection issues, the only elegant and effective means of restoring that, pushing the slab up, is by external post tension. And some people have done. Okay. Now, in external tendon, again two types of tendons are there. In type 1, you can see here the strand, bare strands are just kept inside like this, 7-wire strands, and then you have HDPE pipe that is there. So, this is basically your duct, and then inside that, if you are going for a bonded system, you grout it with a cement grout, or if it is an unbonded system, you fill it with a grease. Okay, that is what we do, right. In the second type of tendon, what we have is they do not have bare strand. These strands themselves will come with a plastic sheathing. So that, like I said, individually also you will have a cover. On top of that, you will also have the duct that is there, right. So, this is a superior system from corrosion point of view. This is superior system. Okay, this is superior system, right. And you have now what we can do, again this also, when you have a bonded system, this inside space will be covered with grout, and if you want an unbonded system, this inside space will be left empty, or they will be filled with grease. Okay, that is what people do. Now, this is again very interesting approach. These are the approaches to the second Vivekananda bridge in Kolkata. You can see these are all dry jointed segmental construction of box girders. They are all done using post tensioning, and you can see this is an example of an external post tensioning where this cables are running outside the concrete, right, and it is a very commonly used method of construction these days in India. Now, from strengthening point of view, this such kind of large pipes, concrete pipes can be strengthened. As you know, when it is transporting water or any form of a liquid, then it is going to generate hydrostatic pressure that is going to create hoop tension, and concrete being weak in tension, it will try to crack. Now, how do you tackle that? By applying circular prestressing, by wrapping a cable around and then stretching them, will create hoop compression in that direction that will nullify the hoop tension that is coming. So, this is a very elegant way of doing structural strengthening. So, this is one way of external PT. Now, again silos are very important structures for use for storing variety of material. Cement silos, coal bunker silos, all very common. Again, over a period of time, they also undergo degradation. Now, if you want to restore them, again external PT strengthening is very common, and this kind of silos can also be strengthened using external PT. So, what you see here, all these cables are basically external PT, right. So, they can be stressed and strengthened. And bridges, again bridges, let us say if you are falling short of capacity or if it is having deflection issues, you can attach a cable from one end to another end and then you stretch them, and that again should follow the bending moment profile, then you create more capacity and recover the deflections. So, this is again external PT is very commonly used for structural strengthening of bridges. And now again harping, again how do you create while you do external PT, again you have to create that point loads where you want, right. So, this kind of harping is a method of holding the cable at a particular profile. For example, I attach this kind of a device so that the cable profile can change like this. Whenever there is a cable profile changing, it is going to push the beam up like this, right. So, in this way, this is here also you see, this is the way that you create this vertical comp. This we will talk in when we talk about load balancing concepts. So, but this is the way that you generate concentrated force through external post tensioning. Now, equipment wise, I think we have said hydraulic prestressing is the most common form of prestressing, and typically people use this kind of a large central hole hydraulic jacks, and these hydraulic jacks, they come with a ram, pump and gauges to measure, and then you have jack stands to hold it at a particular location. Jacks also, you have different types of jacks are there. You have simple jacks for which can do the stressing for one cable at a time, and you can also have a big hydraulic jack like this where you can do a 55 strand cable as well at a time, right. So, you measure the pressure that applied using these hydraulic gauges, and we also measure the elongation in the cable. That elongation in the cable has to be measured, and that should tally with the theoretical calculation. If the difference is more than 5%, then you have something wrong, then you have to go back and check what is going on, right. And this kind of cables are also there. Now, anchorages, again varieties of them. This is the most common type of system that is used in bridges. You can see this is a 9 cable strand, and what you have, this is an anchorage block. This is an anchorage block, and this is a bearing plate, and this is called trumpet, which will help to basically this trumpet will go and connect with the sheathing. Typically, that is how it is done, and the entire system of this prestressing strand, the anchor plate, all these things together, they are called as the tendon. Okay. And this is a system that is used for flat slabs or slabs in general, okay, flat slabs or slabs. Because they are flat, thickness of the slabs are usually 250, 300 or maybe 350. So, for that I cannot have a circular tendon. So, I need to have a flat tendon which is not going to occupy a lot of thickness, right. So, that is the reason we do, and this is a grouting mechanism with which we do. This is a very old system which is called a button head system, where all the individual wires will have this kind of a buttons in the form of a rivet. In that way, it will not let it go. So, this is a wedge based system. This works in the principle of wedge and friction, but this is a different system. This is basically kind of each individual wire will have a rivet form. This is a very old system, not commonly used these days, but this two are very commonly used systems in the modern days. And then we also have, when we want to connect these individual cables together, we also need some intermediate anchorages. For example, you see here, this cable comes and connects and then ends here. Through this anchorage, now I can connect another cable like this and then stretch it from the other end. So, these are called intermediate anchorages. Now, we also have this kind of other intermediate anchorages. Let us say one cable comes and connects here, and another cable can start from here and go. So, in this way, cable can be jointed also using intermediate anchorages. Now, sometimes we also use this fixed anchorages or loop systems. In that way, one end, in the dead end, you can run this kind of a system that itself will lock itself, and then you can stretch it on the other side. So, this is again fixed anchorage or a loop system. By the process, when you loop it at the dead end, it will bond well with the concrete, and it will not come out easily, right. This is a loop system. And this is again bars. This kind of a bars are also used. Okay, heavy bar. These are also sometimes called DV-DAG bars. But typically, when we do the structural testing of large components, we use this kind of DV-DAG bar systems to hold the structural members anchored to the strong floor. And this is called as a trumpet. which will be connecting to the anchor block at the one end, and this side you will be connecting to a sheathing. This side you will have sheathing. So that then the cable will go through that. So these are the different types of system that we use in pre-tensioning and post-tensioning. Now let us summarize what we have discussed. We have discussed in detail about what are the different types of pre-stressing, how do we classify them. We have spent quite a bit of time on what is pre-tensioning and what is post-tensioning, what are the different types of steps involved in pre-tensioning and post-tensioning. We also briefly discuss different types of equipment that are used, particularly the anchorages, and we also discuss the advantages and disadvantages of pre-tensioning and post-tensioning, and we can also combine them to come up with a hybrid system also. So with that, we will end this part of the module. We will continue the discussions in the next part of the module. Thank you.